This is the Chemical Quantities and Calculations screencast. This is part 3 of 3, which is percent composition and empirical formulas. Please have your Chemical Quantities and Calculations handout available for taking notes, as well as the periodic table of elements available for a reference. Percent composition is the percent by weight or mass of each element in a molecular formula. We've already calculated what the grams of each molecule, or actually each element in a molecular formula is. So let's look at an example. We're just actually looking for the percent of each of these weights. So we go through with the normal process. We know in CO2 there's 1 mole of carbon in each molecule of this compound, and there's 2 moles of oxygen, or 2 atoms of oxygen in each molecule. So we take the 1 mole of carbon, multiply it by its molecular weight, 2 moles of oxygen, multiply it by the molecular weight of oxygen. We get 12 grams of carbon, 32 grams of oxygen, for a total of approximately 44 grams of CO2. And that's the molecular weight of CO2. 44.01 grams per mole. Next, we simply take the relative proportions of it. So we know that there's 12.01 grams of carbon. We know the total mass. We multiply it by 100%, and we get 27.29% carbon. We do the same with oxygen. We get 72.7% oxygen for a total value of 100. So really, we're just taking the percent by mass of carbon, percent by mass of oxygen, multiplying it by 100, dividing by the total amount, and that's how we get our percentages. It works the same way no matter how many elements are in the molecular formula. The empirical formula is best described as the simplest whole number ratio of atoms in a molecular formula. So you take your molecular formula, like this one here, C5H10O5, and you can see that it's kind of like your least common denominator calculations in math. You can divide all of these by 5 and still get whole numbers. So the formula, the simplest formula, becomes C1H2O1, and we don't represent ones in a subscript, so it simply becomes CH2O, which is the empirical formula. So it's the simplest formula for the molecular formula. Let's look at a couple of calculations. What is the empirical formula for C4H8? Well, by inspection, both these numbers can be divided by 4, and you get an answer of CH2. Same thing for C8H14. By inspection, both of these can be divided by 2, and you get C4H7. You can no longer divide any of these numbers by a whole number and still get a whole number, so this is the simplest formula. And what is the possible molecular formula for CH2O? Well, I can multiply any of these by a number and still maintain the ratio. Let's try 3. I get C3H6O4. If I used 4, I get C4H8O4. Let's look at another example. A compound has the empirical formula of Sn. If there are 4 atoms of N in one molecule, what is the molecular formula? Well, there's a 1-to-1 ratio of the atoms in this molecule. So if I have 4 atoms of nitrogen in one molecule, that means I have to have 4 atoms of S, or sulfur. So it's S4N4. Let's look at another example. A compound contains 7.31 grams of nickel and 20.0 grams of bromine. Calculate its empirical simplest formula. This is a tiny bit more complex. We take the grams that we know. This is by weight. And if we have grams, we know we can convert 2 moles just using our molecular weight derived from the periodic table. So I multiply these numbers together, I get 0.125 moles of nickel and 0.25 moles of bromine. I've already established my ratio right here. All I need to do now is convert these into whole numbers. So if I divide one into the other, I get 1 molecule of nickel or mole and 2 molecules or moles of bromine. And I can write the subscripts and I get an empirical formula of NiBr2. All this shows is there happens to be twice as many atoms of bromine as there are nickel in this molecule, and that's what this ratio here represents. Let's take a look at one last example. Aspirin is 60% carbon, 4.5% hydrogen, and 35.5% oxygen. Calculate its empirical formula, the simplest formula. So we're going to calculate the moles of each element in 100 grams of aspirin. I'm going to assume an initial weight of 100 grams, so that all the percentages, the calculations involved are easier. So assuming the 100 grams, I get 60 grams of carbon, 4.5 grams of hydrogen, 35.5 grams of oxygen. I take these weights, multiply it by the molecular weight of the element in each case, and I get moles. So I get 5 moles of carbon, 4.5 moles of hydrogen, and 2.2 moles of oxygen. Now let's divide by the smallest number of moles, which was the 2.2, and I start getting my ratio of atoms for the simplest formula. And they're not whole numbers, so I know that I'm going to have to somehow convert them to whole numbers. Just by inspection, I know if I multiply this number by 4, I'll get 9, 8, and another 4. Let's take a look at it. This is indeed what I get, and my answer for the empirical formula is C9H8O4. And if you look at this formula here, it is the simplest with the subscripts being whole numbers. If I divide by any other number while maintaining this ratio, it's not possible. Thank you for watching this screencast.